Welcome to Lesson 2, Example 11. And what they want us to find is the flexural stress, max flexural stress and compression, max flexural stress and tension, the unit stress 3 inches below top of cross section, and to find the section modulus. And first thing I want to say is here's our section. It's 4 inches by 12 inches. We also have to say what's the moment. The moment is equals 80,000, and they put it in inch pounds, which is fine. But the first thing I want to point out is the neutral axis and the centroid. And since this is, I guess, symmetrical above and below the centroid, it's a symmetrical object. It's a square or a rectangle or even an I-beam. You could have an I-beam, and it would be the centroid is the same as the neutral axis. Now you're going to get into certain things where the centroid will always not be the neutral axis. Let's say if you have let's say a concrete beam, and here is your reinforcing steel. What's going to happen is your neutral axis is actually going to be more up here. Let's say right there, even though your centroid of the beam is still, right there. And that's because steel is stronger than this concrete. It has a higher yield stress. So you're going to have this concrete working in compression and this steel working in tension. So these moment arms, and I'll go and do some videos on this later, but it's going to look generally like this, where your neutral axis is where there is no stress. But I know that's kind of confusing. And don't worry about it right now. We'll go over it later. But I just wanted to point out that the neutral axis is not always going to be your centroid. That was the main point of that. Alright, so we're going to go ahead and solve for this equation, or for this problem. And the first thing you want to remember and know is your force. I'm going to call it stress, not force, but stress and bending. And I always put a little b here, so I know it's bending stress. Remember, we had done, if you'll remember, your stress equals P over A. And this is for tension. Or let's just say axial. Axial, which is tension or compression. Things going down the center axis of your cross section, or compression. There we go. That's not the prettiest, but it'll do. And that's the stress. You could call it FA for stress axial equals P over A. This is stress and bending, and it equals MC over I. Or sometimes they say my over I. It kind of depends how you want to look at it and what you're defining MC and my, what they are. And it looks like in the Kaplan study guide here, they say that my and y equals M is always going to be your moment. So here, that's going to be your moment, and that you get that from your shear moment diagrams. You'll figure out what the max moment is. You say, okay, well, that's what I want to design my beam for, my max moment, and that's what comes in here. Your I is your I of your cross section, and this is, this is a rectangular cross section, so it's going to be BH cubed over 12. And now the one thing that might be a little bit confusing is it's either going to be C or I, and the difference is where you're talking about on at what distance from your neutral axis. And in here they're defining y as a distance from the neutral axis to the fiber under consideration. So this, when you're looking at 3 inches down, well, let's say it's 12 inches, so that's going to be 3 inches up from the neutral axis. This actually equals y. While they're defining C, which do they define C? I don't see it right off the bat, but they may do it. C is going to be the distance from your neutral axis to your extreme fiber, I'll call it, or your furthest away from your neutral axis, your top. So that's going to be 6 inches. So MC over I is, or MY over I, you will remember both of them. But the concept is the same. It's going to be your moment times the distance away from neutral axis divided by your moment of inertia. So let's go ahead and solve. And since we're doing the max, we want to find out what the max stress is. And what those stress distributions, I guess is what we're going to call them, is they're going to look like this. Let's change colors here. They're going to, actually, let's make it 3D. That might not be possible at this point. But this is what they're going to look like. And this is going to be the opposite way. So this cross section is in equilibrium if you look at it. This area up here equals this area down here. And this is going to be your max stress, is whatever this is at right here. So this is going to be in PSI or KSI or whatnot. So let's go ahead and solve, and then we'll come over here and put some numbers on these things. And this might not make sense right off the bat, but we'll do some. I know I'll do later videos, and hopefully I can have some time at the end of this video to explain it. So you have M, and you have to watch out for your units. You have inch pounds. And then your C, well, we've already looked at it. C is going to be 6 inches. So we're still in inches. And we had inches over here, so we should be good. Now I, and hopefully you remember what I is. And this is bending. And that's why I put FB. That's what the B stands for, stress and bending. Or you could do F, what you call it, flexural. FF might be a little confusing, so FB is what I put. Alright, but it's really how you define things, and as long as you're trying to be consistent, it helps. But I equals BH cubed over 12, which the base is 4, and actually equals BH cubed over 12 plus AD squared, but remember, we know that AD squared D is going to equal 0 because the neutral axis is the same as that shape. Hopefully that makes sense to you, what I just said. If not, you can work out the whole thing and you'll come up with just BH cubed over 12. Alright, base is 4 inches. Height is 12 inches. We're going to cube that over 12. And we go ahead and put that into the handy calculator. Oh, let's go back. 3 divided by 12. 576 inches to the 4th. Let's see if that's right. 12 cubed times 4 divided by 12. I guess it is. Yes, 576. And that's what they got in on the study guide as well. 576 is your I, so we're going to put that up here. 576 inches to the 4th. Remember to carry your dimensions because that will help you check a lot of things. This is inches, and that just got messy, so let's do that. Alright, let's go ahead and calculate this out. 80,000 times 6 inches divided by 576 equals 833.3. And that is PSI, but let's go ahead and prove that by getting rid of inches. Inch times inch pounds. So we're going to have inch squared, right? Inches times inches divided by 4. So this is going to give you divided by 2 pounds divided by 2 inches squared. So there you go. Pounds over inch squared equals pounds per square inch. All right. So we have 833.3 psi. Let's go ahead and put that up here. 833.3 psi. All right, and that's our max in compression. And this is a positive moment. So here's your beam. You have a positive moment. Positive moment makes a smiley face. hopefully I would read through what the study guide says, and maybe that'll give you a better before I make a video, and I will make videos on this later, but it might be a while. This is going to have tension in the bottom and compression in the top part of the beam. So the top part of your beam is going to be in compression, and the bottom is going to be in tension. And you'll notice that this is 833.3 in for compression. It's going to be 833, and then you'll notice that it's the same equation going for tension. So we just do 6 inches going this way, but everything else is the same. So we're just going to go ahead and write it up here: 833.3 psi in tension. We can go ahead and write this over here. This distribution right here, 833.3 psi. All right. Now let's look at unit stress, 3 inches below. Let's get rid of some of this stuff down here. We already know what our I is. We can get rid of this. And the unit stress 3 inches below top. So at this point we want to say the stress and bending equals my. Remember, because we're not talking about the C is your max, your neutral axis to your top of the flange or top of your section, and Y is where we're talking about. So we have 80,000. This stays the same. Inch pounds. Y is 3 inches, and I is, that's a wiggly line. There we go. Is the same. And that's going to come out to be 80,000 times 3 inches divided by 576 equals 416.7, let's say, psi. And that equals, let's check it, 416.7 psi. And it says 3 inches below the top of the cross section. And remember, the top of the cross section is in compression, the bottom of the cross section is in tension. So that makes sense. And it's kind of hard to visualize and know which one's which, but we'll call this tension. This side is going to be tension. This side is going to be compression. Alright, so we're looking right here, halfway up, and you're saying that this is 416.7 psi. And does that make sense? Well, yeah, it's halfway up, so this is, what, 3 inches from the neutral axis. This, where it hits 0, is your neutral axis, and always will be 3 inches, and then this is 6 inches. Well, you can say, well, that's a linear line. Let me throw in a quick equation. And you know that, well, 0 is right here, and you know it's going to 813 over 6 inches. So you want to say, well, that's 833 divided by 6. And that's 138.889, let's say, times your x, your distance up. And our distance is 3, so when x equals 3, let's say 138.9, let's just do that, times 3 inches equals 416. So that makes sense. And that's just doing an equation from here to there to make sure that we're good. And we are. And it makes sense. So we're good to go there. All right. And that is what the unit stress is. So this answer is 416.7 psi. Remember, IS is the section modulus equals I over C, which equals 576, whoops, 576 inches to the 4th divided by 6 inches equals 96 inches to the 3rd, because you have inches to the 4th divided by inches. You just get rid of one of those. You cross out one of these and say, okay, I now have 3. And there you go, 96 inches to the 3rd.